In this video, we are going to be learning more about the center of mass. This video is specifically about the calculus version of the center of mass. So like you would do with regular center of mass or non-calculus version of the center of mass, you would find the x, y, and z coordinates separately. This is the calc equation given to you in the x direction just as an example. It would be 1 over the mass of the object, and then you take the integral of x times dm. Now, one thing that will help us with finding the center of mass using the calculus version is learning about different kinds of densities. So we know D equals m over v. That's actually called volumetric mass density. That's mass per unit volume. In physics, the symbol rho, which is a Greek letter, is used. So the volumetric mass density is rho, which is m over v. There's also surface mass density. That's mass per unit thickness of a sheet of uniform thickness. And that is where this is the Greek letter lowercase sigma. So sigma would be equal to the volumetric mass density times the thickness, or you can also think of it as the area of an object divided by its mass. There is also linear mass density. It's mass per unit length of a rod of a uniform cross-sectional area, and the Greek letter lambda is used there. Lambda is equal to mass divided by the length, and it would also be the same as the volumetric mass density times the area. Here is an example of finding the center of mass using the calculus version of the formula. We are going to be finding the center of mass of a rod of uniform density. Now, we actually kind of already know what the answer should be. We saw that with the ruler when we balanced the ruler in class. The center of mass should be right in the center. So technically, the center of mass should be the length of the thing divided by 2, so L over 2. So we should get L over 2 as our final answer. Here's how you use calculus. So first, it's established that the rod has a mass capital M and length capital L. Because of that, we know that it has a linear mass density of lambda equals m over L, so mass per length. Here is a picture that should help us out. So what we've done here is we've placed this uniform rod along the x-axis. We can assume that the thickness and the y height, the height in the y direction, is pretty much negligible, or that it's even on all sides, so that the y coordinate of the center of mass doesn't matter. We will be looking for the x coordinate for the center of mass. So again, we are finding the center of mass along this x-axis here. Now what we've done here is we've said, okay, here is an area of this rod, and this rod has a length of dx. Remember, d from calculus stands for a small change. So we've divided, essentially what we've done is divided up this rod into tiny sections. Now, each of these tiny sections will have a mass of dm. Remember, again, d stands for a small change, so a little bit of mass corresponding to a little bit of thickness or length. And we know that the linear mass density will be equal to dm over dx because it's m over L. So just a little bit of mass divided by a little bit of length will equal the linear mass density. And we know it has a uniform density, so this should hold all across this rod. If we rearrange what I have here just a little bit, you'll get that dm is equal to lambda times dx. And that's important because we want to plug it back into our formula, okay? We can't integrate this right now because this is our variable, but we want to integrate it in terms of another variable. So somehow we have to find a way to relate dm to x, which we did right up here. Sorry for my bad circling. We are going to plug this in right here. And we also know we want to take the integral from 0 out to L, because the rod has a length of L. So these are our integral boundaries. Okay, so now we have 1 over m, which we can leave outside the integral, times x lambda dx. So we're taking x and integrating it in terms of dx, so that's helpful. And lambda is a constant. We can just take that out of our integral. And if you integrate this, you'll end up having x squared over 2. So if you take the derivative of x squared over 2, well, you use the power rule, so you would end up with 2x over 2, so you would end up with just x if you take the derivative of that. Okay, now we have to evaluate this integral from 0 to L, so you plug in L and then subtract it when you plug in a 0. So you'll have 1 over m lambda over 2L squared minus 1 over m lambda over 2 0 squared. Obviously this term will just go away because it's 0. And then you'll end up with 1 over m lambda over 2L squared. I plugged in m over L for lambda because that's what we knew from the very beginning of the problem. Now some stuff will cancel out very nicely, so you'll have this m and this m cancel out, and then this L will cancel out with one of the L squareds, so you'll end up with L over 2. And that's how you use the calculus version of the center of mass.